Polynomial functions, section 3.3 to 3.4, example 6. Factor the polynomial over the ring of integers. F of x is x to the fourth plus 2x to the second minus 63. Since this is quadratic in form, we can factor it like a quadratic function. We can write x to the fourth as x squared squared. And then copy the rest of it, 2x squared minus 63. And then we'll do a substitution and replace x squared with u. So we're going to let u is equal to x squared, and that'll give us u squared plus 2u minus 63. And then we can now we can factor this like a quadratic function. U times u will give us u squared, and we need two numbers to multiply to negative 63 and add up to 2. And what works is negative 7 and positive 9. And you can check with the FOIL method. If you do first times first, u times u is u squared. Outer product is 9u. Inner product is negative 7u. 9u minus 7u gives you the middle term, which is 2u. Last times last, negative 7 times 9 is 63. And now we can replace u by x squared again. So this is going to be x squared minus 7 times the quantity x squared plus 9. Okay, so now we've factored that. And that's as far as we can go with integers. We will see in the next examples that if we use numbers other than integers, we can actually break this down a little bit further. Okay, so let's go on to the next example. This is going to be the same function, except now we want to factor this over the field of real numbers. So from the previous example, we know that f of x is x squared minus 7 times the quantity x squared plus 9. And we can set f of x equal to 0 to get the x-intercepts, or the zeros of the function. So we have a product equal to 0. That means one of the factors is 0. X squared minus 7 equals 0, or x squared plus 9 equals 0. And if we solve for x, we'll add 7 to both sides. We get x squared is equal to 7. Subtract 9 from both sides. We get x squared equals negative 9. Now, the square root of negative 9 is not a real number, but the square root of 7 is. We can take the square root, and there's actually two square roots, so x is equal to either negative square root of 7 or positive square root of 7. Okay, so those are the x-intercepts, or the zeros, or the real zeros of this polynomial. Okay, so then square root of 7 is going to be 2 point something. It's not an integer, but it's a real number. The third step now is to use the x-intercepts to factor f of x. Okay, so we have we start with our answer for step 2, x equal negative root 7, x equal positive root 7, or the other one, the other factor is x squared plus 9 is equal to 0. If we add root 7 to both sides here, we'll get x plus root 7 equals 0. Subtract root 7 from both sides, we have x minus root 7 equals 0. X squared plus 9 equals 0. So then the zero product rule says the product is equal to 0. So that means that x plus root 7 times the quantity x minus root 7 times the quantity x squared plus 9 equals 0. So that means that f of x is this is going to be this product, x plus root 7 times the quantity x minus root 7 times the quantity x squared plus 9. Okay, so that's the answer to this question. And that's as far as we can go with real numbers. But we'll see in the next section that this last factor can actually be broken down further if we use numbers other than real numbers. So let's go on to the next example. Okay, the same polynomial, and now we want to factor it over the field of complex numbers. So from our previous answer, we factored over the field of real numbers to x plus root 7 times the quantity x minus root 7 times this quantity x squared plus 9. And because the degree of the last factor is more than 1, we have degree 2 here, we can break down this last factor further. We want to solve x squared plus 9 equals 0, and subtract 9 from both sides. That means that x squared is equal to negative 9, and then take the square root. So x is going to be plus or minus square root of negative 9. Now we can write this as plus or minus square root of 9 times the square root of negative 1, because negative 9 is equal to 9 times negative 1. Square root of negative 9 is an integer. We know what that is. That's 3, because 3 times 3 is 9. So this is going to be plus or minus 3. And square root of negative 1 is an imaginary number. We use the letter I to represent the square root of negative 1. So x is equal to either negative 3i or positive 3i. And then, so then we can use these zeros to break down the last factor. So if we solve these for 0, add 3i to both sides here, we get x plus 3i equals 0. Or here we'll subtract 3i from both sides. X minus 3i equals 0. So that means the product is equal to 0. So that means that the quantity x plus 3i, x minus 3i equals 0. And so the last factor is x plus 3i times x minus 3i. And if we put it together with the other factors, we have f of x is equal to x plus root 7, x minus root 7, x plus 3i, x minus 3i. And that's as far as we can go. And just a comment here, the fundamental theorem of, let's answer this problem. Fundamental theorem of algebra states that a polynomial of degree n, in this case we had degree 4, factors into exactly n linear factors. In this case it's 4 linear factors, 1, 2, 3, 4, over the field of complex numbers, possibly including duplicates, and has exactly n zeros over the field of complex numbers, possibly including duplicates, corresponding to these n linear factors. So, in this case we have the polynomial of degree 4, so we've had exactly 4 linear factors. Okay, so that concludes this presentation.